I want to start with a provocation that sounds, well, it sounds philosophical, but I think for anyone working in distributed systems, it's actually a distinct source of trauma.
Oh, I know where you're going with this.
How do you define now?
It's the most deceptive three-letter word in engineering. It really is.
Right, because in our daily lives, now feels so absolute. You check your phone, it's 2:00 p.m. I check mine, it's 2:00 p.m. We assume it's the same now for everyone.
We take it for granted.
Exactly. But we've got a stack of documents here from a company called Roxy Systems, specifically their Chronos Manifesto, that argues this very intuition is not just wrong, it's arguably the biggest architectural flaw in modern computing.
They're calling it the Newtonian trap. And honestly, it's a fair critique, a really sharp one.
It seems like it. I mean, we spend so much energy, so many cycles trying to synchronize clocks across servers.
All day, every day, relying on NTP, network time protocol, just hoping that now in a data center in Virginia is close enough to now in Tokyo.
But the reality of physics, just the sheer speed of light and network latency, it makes that a fool's errand. A perfect sync is impossible.
It's fundamentally impossible. You're always chasing it.
So that's the mission for this deep dive. We're going to dismantle that idea of absolute time. We're looking at how Roxy Systems is proposing a philosophical shift from what they call archival thinking to operational thinking.
And more importantly, how they've built a system to enforce it. The Chronos Ledger.
Right. A system that uses relativistic physics, of all things, to guarantee truth without needing a building full of atomic clocks.
It's moved from trusting the wall clock to trusting the sequence. It's effectively weaponizing Einstein's special relativity to solve things like the double spin problem. It's a pretty wild concept.
Okay, so let's start with that distinction they make right at the top of the manifesto. They draw this really hard line between archival data and operational data. To me, data is data. Why does this distinction matter so much to them?
I think it's about the direction of the gaze. The archival mindset, which is how, most traditional databases function, is historical. It asks the question, what happened?
Right. You're querying a pile of static records from the past.
Exactly. But the operational mindset, it asks a totally different question. It asks, what is happening right now? It's trying to capture the live beating pulse of the system.
But isn't what happened just the accumulation of what is happening? I mean, aren't they just two sides of the same coin?
In a perfect world with a single computer, yes. But in a distributed system, there's a gap between those two questions. A very dangerous gap.
Okay.
When you ask what is happening, you're usually trying to make a decision. A critical decision. Do I authorize this trade? Do I lock this inventory item? Do I sell this last seat on the plane?
A decision that has consequences in the real world.
Exactly. And if your answer relies on an archival method like looking at a timestamp that might be stale, even by a few milliseconds, you can make the wrong decision. You sell the same seat on the plane twice.
Which brings us to their Newtonian trap. The standard engineering impulse, the thing we all learn, is to say, okay, we need to know what happened first, so let's just look at the timestamps.
It's intuitive. Machine A writes at 12:00.01. Machine B writes at 12:00.02. Obviously, A came first.
And that works beautifully if A and B are, in the same room, connected to the same motherboard.
But scale that out across the globe. You've got servers running on different hardware and different climates, subject to different heat loads, different vibrations even.
The crystal oscillators inside the computers.
Exactly. The little piece of quartz crystal in a server motherboard that vibrates to keep time. It isn't perfect. It's a physical object. It drifts.
So my second might be a tiny bit longer or shorter than your second.
It might drift a few milliseconds a day, and that doesn't sound like much, but in high-frequency trading or global transactional ledgers, a millisecond is an eternity. It's a difference between profit and loss.
And even if you run NTP, the network time protocol, you're not fixing the drift, are you? You're just constantly correcting for it.
That's a great way to put it. You're never actually at the correct time. You're just hovering around it. You're constantly getting these little nudges. Speed up a bit, slow down a bit.
You're oscillating around the truth.
You are. And then you add the big killer, network latency. This is the simultaneity paradox the manifesto highlights so well.
Okay, so let's walk through their example.
Let's say machine A, maybe in New York, sends a signal at 12:00.01. And machine B in London sends one at 12:00.00.
So in a Newtonian universe, a world with perfect clocks and instant communication, B is clearly first, no question.
But what if B is in a slow network zone, or its packets get routed through a congested switch in some data center in Iceland? It's entirely possible that the central database receives A's message first.
So the database sees A, then it sees B. But the timestamps on the messages themselves say B, then A. The system is now in a conflict state.
It's in a state of paradox. Which reality do you trust, the arrival time or the timestamp?
If you trust the timestamp, the Newtonian view, you might be trusting a clock that was 50 milliseconds slow.
And if you trust the arrival time, you're ignoring when the user actually clicked the button. The manifesto argues that relying on wall clock time for ordering events in a distributed system is just a fallacy. It breaks this critical property called linearizability.
Okay, linearizability is a term we throw around a lot, but let's be really precise here. We're talking about the system appearing to the outside world as if it were just one single machine processing one thing at a time, in order.
Correct. It's the illusion of a single-threaded reality. If I deposit $100 and then immediately transfer it, linearizability guarantees that everyone in the system everywhere sees the deposit before they see the transfer.
And if you don't have that guarantee,
You get chaos. You might see the transfer first, which triggers an overdraft fee, even though, you actually had the money. The system's view of reality is momentarily scrambled.
that's the nightmare scenario.
Yeah.
So Roxy Systems says, stop looking at the clock, just abandon it. And they pivot to Einstein. Now, I know the basics of special relativity, time is relative to the observer, but how does this actually help us sort a database?
It helps because it forces us to accept that there is no God's eye view of the system. There's no privileged observer. In physics, if two events happen far apart, there is no absolute truth about which happened first, unless one caused the other.
Unless there's a connection between them.
Right, and that connection is where we cross what I call the Lamport bridge.
Leslie Lamport, a giant in the field that happens before a relationship.
The godfather of distributed systems. Lamport had this incredible insight back in the 70s. He realized that since we can't synchronize clocks perfectly, we should stop trying. Instead, we should synchronize causality.
So if event A causes event B,
Then there must have been a message passed from A to B. There has to be a flow of information.
the speed of light constraint, but for computers.
Exactly. Information cannot travel faster than light. In a computer system, information cannot travel faster than the network latency. So if machine A does something and never tells machine B about it, then as far as machine B is concerned, that event hasn't entered its reality yet.
They're concurrent events. They exist in their own separate timelines, in a way.
They're causally disconnected. So instead of trying to force a global timeline on things that are disconnected, we only track the causal links. I received a message from you, therefore what I do next happens after what you did. It's a much more humble and more accurate way of looking at time.
It makes sense, but here's the problem, right? Databases need a total order, eventually.
They do. That's the rub.
You can't just have this web of partial causality. Eventually, you need to print a bank statement that lists transactions 1 through 10. You have to. You have to collapse the wave function, to borrow a term from another part of physics.
You have to make a decision, and this is where the atomic sealer comes in. This is the absolute heart of the Chronos architecture. The manifesto describes this as the system's inertial frame.
An inertial frame, like in physics, a non-accelerating frame of reference.
That's the key architectural decision. Since the universe doesn't provide a single universal frame of reference for our distributed system, Roxy Systems says, fine, we'll build an artificial one. That is the atomic sealer.
And its rule is absolute.
Utterly. It doesn't matter what time it is on the client machine in Australia. It doesn't matter what the network latency was. The only truth that matters is the order in which the sealer accepts the inputs. Full stop.
It sounds kind of authoritarian.
It is. It has to be. The sealer is the benevolent dictator of the timeline. It's the central observer that collapses all possibilities into a single immutable history.
They use a specific phrase here that I love. The future light cone. Once the sealer stamps an event with a sequence ID, it enters the future light cone.
I appreciate that terminology, too. In physics, an event's future light cone represents all points in spacetime that can possibly be affected by that event.
So by using that term, Roxy is saying something very specific.
They're saying, once this event is assigned a global ID, say ID number 42, it is now an unchangeable historical fact. Every subsequent operation, 43, 44, and so on, must acknowledge that 42 happened. It's now part of the causal fabric of the system.
So truth shifts. It's no longer a question of when did this happen. It's a much simpler question.
It becomes, what is its sequence ID?
If I have ID number 100 and you have ID number 101, I happen before you. Period.
Even if your local clock was 5 minutes fast and mine was broken, the sequence is the only truth that matters.
Okay, that's the theory, and it's elegant, it's physically sound. But let's get into the machine they actually built to enforce this, the Chronos Ledger.
Right, the implementation.
Because they make this huge claim that they can achieve this strict linearizability on commodity hardware. And let's be honest, that's a massive dig at Google Spanner, isn't it?
Oh, it's a huge dig. It's a shot right across the bow. Google Spanner is an engineering marvel, but it solves this problem with brute force and a lot of money.
With their TrueTime API.
Right. They literally put atomic clocks and GPS receivers in their data centers to shrink the window of clock uncertainty down to a few milliseconds. It works, but it's incredibly expensive. And, it locks you into Google's infrastructure.
If you want Spanner consistency, you pay Spanner rent.
You do. Roxy is claiming they can give you that same mathematical guarantee, but using standard off-the-shelf servers. And they do it with this three-part architecture, VEPS, the ImmutableLedger, and Constraint.DB.
Let's break these down because the magic seems to be in the interaction between them.
It is. Let's start with VEPS, the Verification and Event Processing Service.
They call it the intelligent filter, but reading the description, it acts more like a firewall for business logic.
I think of it as the event horizon of a black hole. Nothing gets into the ledger, into the singularity of truth, without passing through VEPS.
And it's not just checking if the JSON is formatted correctly.
No, it's stateful. It's checking the actual state of the system. This is where they implement what they call fractal CP.
We should probably unpack fractal CP. That's a clear reference to the CAP theorem: consistency, availability, partition tolerance. And the classic rule is you can only pick two.
Usually, yes. When your network gets partitioned, when servers can't talk to each other, you have to choose. Do I keep accepting writes, which is availability, and risk getting conflicting data? Or do I stop accepting writes to keep the data pure, which is consistency?
And fractal CP implies they are making that choice, but at a very specific layer.
Exactly. At this specific layer, the VEPS layer, the front door, they brutally, ruthlessly sacrifice availability for consistency.
So it's a veto service.
It's an absolute veto service. If VEPS cannot confirm with 100% certainty that you have the funds in your account or that the inventory item exists, it vetoes a transaction. It blocks the write.
So it would rather fail your request than let a maybe into the system.
It would much rather say no or try again later than risk polluting the ledger with a state that might be proven wrong a millisecond later.
They mentioned a 50 Miller's finality here. This is the tempo, the heartbeat of the system. If consensus isn't reached in 50 milliseconds, the system times out and blocks the release.
It enforces a strict rhythm.
Now, playing devil's advocate, 50 milliseconds in the world of high-frequency trading, that's an eternity. HFT firms fight over microseconds. Isn't this too slow for that world?
For certain kinds of HFT arbitrage, yes, probably too slow. But for a global banking ledger, a supply chain system, a medical record database, 50 milliseconds is effectively instant to a human user.
We can't perceive that delay.
Not at all, and the trade-off is critical. By enforcing that 50 millis wait, they are ensuring that every node in the cluster has time to gossip and agree. They are prioritizing safety over raw, bleeding-edge speed.
It's a statement.
It's a statement. They're saying, we will not be the fastest database in the world, but we will be the one that is never wrong.
And that's a very distinct market position. We are the database that is never wrong. Okay, so VEPS gives the thumbs up. It says, this transaction is valid. It passes it to the core, the immutable ledger.
This is it, the single source of chronological truth. This is where the sequencing actually happens. Under the hood, they're using well-known consensus protocols. The manifesto mentions Raft, or Paxos.
Let's talk about that mechanism just for a second, because consensus sounds very democratic, like they all sit around and vote. But in a protocol like Raft, it's a leader-follower model, isn't it?
It is. It's more efficient that way. In a Raft cluster, one node is elected as the leader through a little election process. All writes from VEPS go to that one leader.
Okay, so the leader gets the new transaction.
Right. The leader says, okay, I have a new entry. User A sends $5 to user B. I am assigning this global ID number 500. The leader then writes that to its own log and broadcasts it to all the follower nodes.
And the followers have to acknowledge it. They have to say, yep, got it.
But not all of them need to. That's the key, just a quorum. So if you have a 5-node cluster, you only need 3 to agree, the leader plus 2 followers. Once the leader gets those acknowledgments, the entry is officially committed. It's sealed. It's permanent.
What happens if the leader server, catches fire right after it receives the request before it can replicate it to a quorum?
That's the beauty of the protocol. The client, the person who sent the transaction, won't receive a success confirmation until that quorum is reached.
Ah, okay.
So if the leader dies mid-process, the followers will quickly realize the leader is gone. They'll hold a new election, pick a new leader from among themselves, and since the old right wasn't committed, it effectively never happened. The client gets a failure notification. Try again.
So the system effectively rewinds that little piece of uncommitted reality.
Exactly. No fandom data, no maybe states. It either commits to a quorum or it fails cleanly.
Okay, so we have the ledger. It's this perfect linear sequence of events, global ID 1, 2, 3, all the way to infinity. But querying a sequential log like that is incredibly inefficient.
That's terrible for reads.
If I want to know my current account balance, I don't want the system to have to replay my entire history of transactions every single time I open the banking app.
That would be what we call ON complexity. It would grind to a halt as soon as you had any significant amount of data. This is precisely why they built the third component, Constraint.DB. This is the observational model.
This sounds a lot like a pattern called CQRS, Command Query Responsibility Segregation.
It is CQRS, absolutely. But it's CQRS with a specific relativistic flavor. The core idea is to completely separate the write model, which is the immutable ledger, from the read model, which is Constraint.DB.
So the ledger is optimized for one thing and one thing only, putting events in order safely.
And Constraint.DB is a projection, a materialized view of that ledger. It's optimized for one thing, looking things up fast. It might be a traditional SQL database or a key value store, whatever is best for the queries you need to run.
But there's a physical gap there, a literal distance in the data center and a time gap between the ledger sealing an event and that event showing up in the read model. That means there's lag.
There is. And Roxy doesn't hide from this. They embrace it. They have a great term for it. Eventual consistency with causal integrity.
Now, eventual consistency is usually a dirty word in banking. It implies that for a few seconds, my balance might be wrong.
And that's where we have to be really precise. Let's distinguish between data being stale and data being wrong.
Okay, what's the difference in their world?
Wrong means the data is corrupted or out of order. It's seeing a reply to an email before you see the email it's replying to. That's chaos. That breaks logic.
And stale.
Stale just means you're looking at the very recent past. You're looking at a perfectly consistent, accurate snapshot of reality from, say, 20 milliseconds ago.
So Constraint.DB might be 20, maybe 50 milliseconds behind the absolute truth in the ledger.
Right. But because it processes the events using the global IDs from the ledger, the order is always preserved. The database will never apply update number 501 before it has applied update number 500.
It might pause at 499 for a few milliseconds while it waits for 500 to arrive from the ledger.
But it will never skip ahead and create a nonsensical state.
So the user experience is consistent. I might not see the money I just deposited for the blink of an eye, but I will never see a chaotic world where the math doesn't add up.
Exactly. And for the user, that 50-meet lag is completely imperceptible. But for the system architect, it means you can scale the read side of your system infinitely. You can have thousands of Constraint.DB nodes, receiving millions of users, all being fed by that one single strict ledger.
It effectively decouples the speed of truth, which is the writes, from the speed of access, which is the reads.
Which is really the only way to build a planetary scale system that is both incredibly fast to read from and mathematically safe to write to.
Now, I want to pivot to the security aspect of this. Part 4 of the manifesto talks about mathematical integrity. And this is a huge deal. We're living in an era of supply chain attacks, insider threats. What if a rogue admin with root access decides to just rewrite history?
Oh, look, I actually had $10 million in my account yesterday.
Yeah, how do you prevent that?
This is where Roxy Systems moves from being a database company to almost a crypto forensics company. They don't rely on access controls and permissions alone. They rely on cryptographic hash chaining.
This sounds a lot like blockchain technology.
It borrows the core primitive, the most important idea from blockchain, the Merkle chain concept. It's brilliant. Here's how it works.
Okay.
Every entry in the immutable ledger isn't just a piece of data. It's a cryptographic object. When entry number 500 is written, the system takes all the data, user A, $5, and it combines it with the unique digital fingerprint, the hash of the previous entry, entry number 499.
So entry 500 essentially contains a little piece of its parent, entry 499.
Exactly. It says,
Yeah.
I am this transaction, and I am the direct child of entry 499. Then it runs all of that combined data through a SHA-256 hashing algorithm to create its own new, unique fingerprint.
And SHA-256, that's the industry gold standard for this kind of thing.
It's the gold standard, and the key property of SHA-256 that makes this whole thing work is something called the avalanche effect.
Avalanche effect.
It means if you change a single bit of data in the input, if you change $5 to $5.01, a tiny change, the resulting hash changes completely. It doesn't just change a little. It looks like a totally different random string of characters.
Okay, so let's play out the attack. I'm the rogue admin. I root on the server. I want to go back in time and change entry number 400.
All right. You use your admin powers, you go into the hard drive, you change the bits in the data file for entry 400. Now, instantly, entry 400 has a brand new hash, a new fingerprint.
The next entry in the chain, entry 401.
Entry 401 contains the old hash of number 400. So now the chain is broken. An auditor, or even the system itself, looks at 401 and says, wait a minute, you claim your parent's hash is X, but the record at position 400 now has a hash of Y. Validation fails. The tampering is obvious.
So to cover my tracks, I have to update entry 401 to point to my new fraudulent version of 400.
Which then changes 401's hash, which breaks the link with 402.
So I have to rewrite 402 and 403.
You would have to rewrite every single event, every single cryptographic link, from the moment of your fraud all the way up to the present millisecond. And if this system is replicating its ledger to other nodes in real time,
I'd have to perform that massive rewrite on every node in the cluster all at the same time, faster than the network can propagate the real, valid next block.
which is computationally impossible. This is what makes the ledger forensically complete. You don't need to trust the bank manager anymore. You can audit the chain. If the hashes line up, the history is mathematically proven to be unaltered.
This is what they mean by relativistic verification. The history is locked in, not by a password, but by its own causal cryptographic chain.
It's building trust through math, not through authority. It's a really powerful idea.
So bringing this all together, we've gone from the random drift of quartz crystals to the inertial frame of the sealer. We've passed through the event horizon of VEPS, and we finally locked it all down with SHA-256. Why does this architecture matter so much right now? What is the so what for the industry?
I think we're reaching a breaking point with the good enough approach to data consistency. For the last decade, maybe more, the mantra in Silicon Valley was move fast and break things.
Right.
And we accepted eventually consistent databases because we were building social networks and photo sharing apps. If a tweet shows up out of order or takes a second to appear, nobody dies. Nobody loses their life savings.
But that's not the world we're building anymore. Now we're moving everything to the cloud. Real-time payments, medical diagnostics, autonomous logistics for shipping fleets.
Exactly. Move fast and break things doesn't work when you're managing a nation's power grid or a stock exchange or a hospital's inventory of medicine. Roxy Systems seems to be betting that the next wave of critical infrastructure needs to be move fast, improve things.
That's a great line. It's a shift from optimistic architectures, I hope the clocks are synced, to pessimistic, verifiable architectures.
It's an architecture that says, I assume the clocks are wrong, I assume the network is unreliable, so I will enforce order through consensus and lock it with cryptography.
And the fact that they are doing this on commodity hardware is the real disruptor here.
That's the part that I think will scare the big cloud providers. They are democratizing financial-grade consistency. You don't need a Google-sized budget or a rack of atomic clocks to have an unimpeachable source of truth. You just need the right architecture.
It's the democratization of linearizability.
That's a mouthful, but yes, that is exactly what it is.
There's a philosophical layer to this that I want to end on.
Yeah.
We started this whole deep dive by asking, what time is it? And I think we've realized that the question itself is flawed, at least for distributed systems.
It is. The Chronos Ledger suggests that time, in the digital sense, isn't a measurement we discover. It's an agreement we make.
That's the profound takeaway for me. We tend to think of truth, with a capital T, as something objective that we discover. I looked at the clock and I found the time.
But in these complex distributed systems and, maybe in society in general, truth is something we construct.
We construct it by agreeing on the sequence of events.
Right. The very name, the atomic sealer, implies that reality is a negotiated settlement. The system's nodes agree that event A happened before event B, the sealer seals it with a hash, and that becomes immutable history. It forces us to ask a really uncomfortable question. In our own lives, outside of computers, who acts as the sealer?
That is a heavy question, because we rely on institutions, news organizations, courts, historians to be our atomic sealers, to timestamp reality for us and put events in an agreed-upon order.
And just like in the distributed system, if we don't have a consensus protocol, if you don't agree on the basic order of events, we end up with a split-brain scenario.
Where half the country sees one reality and the other half sees a completely different one.
And without that cryptographic chain, without that shared set of facts linking us to a shared past, the network partitions.
The society partitions.
That is the danger. You know, the Chronos Manifesto is technically a paper about databases, but it's arguably a blueprint for how any distributed group of entities, whether they're servers or people, can maintain a coherent shared reality. You need a mechanism for consensus, and you need a mechanism to lock it down so it can't be rewritten on a whim.
That is a fascinating, if slightly terrifying place to land. From database shards to the very fabric of social reality.
It's all connected. The patterns are the same.
We're going to leave it there. For everyone listening, whether you're an architect debugging a race condition in your code, or just someone trying to understand why your bank balance takes a second to update, hopefully this gives you a new appreciation for the managed chaos under the hood of our digital world.
And remember, watch out for the Newtonian trap. It's everywhere.
Always. This deep dive was custom built for you. Thanks for listening.